Hello students, I want to talk about equilibrium and ice tables. Um, that you've learned before that there's certain driving forces for reaction, namely formation of a solid or a gas, or formation of a covalent compound. In other words, for a reaction to occur when you mix a couple things, you got to make sure that not everything is a spectator. So there is a net ionic equation. In other words, the reactants and the products are not the same. Take a reaction. Calcium carbonate can be formed by a solution of calcium plus 2 ions and carbonate ions. Now, I'm leaving out the spectators, and you know carbonates are insoluble for the most part, so you form calcium carbonate solid, and that's how you write the equation, right? But it's a little bit of a lie, okay? We simplify things because, there's layer upon layer in chemistry. So this really isn't the end of the story. The calcium carbonate doesn't just sit there and never redissolve. There's always some little bit of action going on. The calcium carbonate, to some extent, redissolves, even if it's just a little tiny bit. And you use equilibrium expressions, K, numbers, to express how much of the ions are in solution. Okay, because sometimes it makes a big difference. I mean, if you have calcium, I mean, you can even think of it in your bloodstream. It reacts with oxalate, that's what gives you gallstones. So you really want to know how many ions are in solution from an insoluble compound. So all these insoluble compounds have equilibrium constants associated with them. So there's the calcium carbonate redissolving into calcium ions and carbonate. It's a forward and a backward process. Okay, it's a dynamic process. There's always some molecule or some formula unit, if you will, of calcium carbonate dissolving, and some different calcium ions and carbonate ions that are in solution reforming the calcium carbonate. Okay, and that's called dynamic equilibrium. And that occurs for insoluble compounds. It really occurs for the things that we've been telling you, well, there aren't any ions in solution. Well, there aren't many, but there are some. So the equilibrium constant K is the products, of course, over the reactants. And the products are soluble ions, and the reactants are solids, so only the products appear. So in this case, it's going to be called a KSP, K solubility product, because it's really just the product of the calcium ions times the carbonate in the numerator, and in the denominator, there's 1. There's nothing. Okay? So, it doesn't appear, it doesn't mean it's 0, it just means we put a 1 there. What is the concentration of a solid? We just call it 1. So we just call that the solubility product. So what am I writing here? So solids don't appear, and pure liquids don't appear either. Okay, because again, what's their concentration of the pure liquid? I guess it's the density divided by the volume, but we're not putting that in there. We're just putting the molarity of things in solution. Okay. So again, the equilibrium constant in this case is a KSP, and it's for calcium carbonate solid, and it is, you look it up. You can look up in the back of your book, in the appendix of any book, KSP values for insoluble compounds. In this case, it's 9.3 times 10 to the negative 10th. No units. I know I'm lazy and I usually don't write units, even if there are, but there really are no units in equilibrium constants, which is kind of nice. Okay, so let me write this again. I'm telling you it's small. It's a small number. It's an insoluble compound. And then let me set up this ice table I've been telling you about. Ice stands for initial, change, and equilibrium. So it's going to be the concentrations initially, how much they change, and at equilibrium. Now we're really only interested in the equilibrium values, and if we had those, we'd just plug them in to the equation and be done. But usually you have to do some calculation. Okay, so I guess I'm writing this again. If you haven't seen it before, here it is again. No, I haven't fallen asleep yet. Wish I knew how to speed this up. That's the next thing I have to learn, isn't it? So this expression is, oh my gosh, what is it? The solubility product. And that is a kind of equilibrium constant. Except it's not really a ratio because the denominator is 1. Okay, so if this is the number, oh, let's see. Let's just hope. If only this were faster. If the only source, yes, here's what I'm going to say. If the only source of calcium plus 2 and the carbonate anion is calcium carbonate redissolving, then the calcium ion concentration and the carbonate anion concentration are equal. And that's what I'm going to say. So, wow. Yeah. Then, like that. Okay, so there you can see it written out. Calcium ion concentration equals, now she's made a mistake, hasn't she? Carbonate ion concentration. They are the same. And so your KSP, you're going to find out is equal to a number squared. And then what am I saying? Oh, okay, now this is about the solubility, and this is important. The amount of calcium carbonate that goes into solution, we know it's an ionic compound, metal and nonmetal, so it dissolves. So the amount or the solubility of the calcium carbonate, or the amount that dissolves, that's why I put a delta, is going to equal the amount of calcium plus 2 that appears and carbonate that appears. I think we don't talk about that enough, but if some of the insoluble, quote, insoluble compound dissolves, manages to get into the water layer, it's going to dissociate into ions. And that's what the meaning of a strong electrolyte is, whether or not it's soluble or not. All ionic compounds are strong electrolytes. So here's the ice table. I sure hope this is recording because, yeah, like that. Okay, so the calcium carbonate, the reversible reaction, it's reversible even though it's mainly the reactant that we have here. And you always write the solid on the left for KSP. Now let's turn this into a simple kind of ice table. Okay, so you can use that. Now, since equilibrium constants are in concentration, we're going to use molarity in the ice table. We could use ice tables for stoichiometry, and I wish we would, and just use moles. But in this case, for equilibrium constants, we've got to make sure everything is in concentration and not moles. So we got to divide by the volume. Okay, so calcium carbonate, I don't know what it is. It's a solid. And I'm always going to assume for these, well, unless told otherwise, that there is no ions. We're going to just start initially. Okay, initially no ions. But then some calcium carbonate does make it into solution, breaks up into ions. So I've got negative X and positive X for the carbonate, the calcium ion, and the carbonate ion. Okay, so that is equal to the KSP. So calcium ion concentration times carbonate, which is X times X, or X squared, equals the KSP. And so if I take the square root of the KSP, I will know what X is, which is the concentration of both the ions in solution. They are both the same. It's approximately, 3 times 10 to the negative 5th molar. Okay, so when asked what is the concentration of ions in solution for an whatever compound, an insoluble compound, you can set up an ice table. Okay, now this is the simplest kind because there's one of each kind of ion. There's one calcium and one carbonate. So I don't have to worry about any coefficients. I don't have to worry about any exponents. Each of them are just x. And they're that number. Ta-da!